Hello everybody. In this video we are going to talk about the fundamental principles of classical mechanics, or the mechanics of a particle. In the next video we are going to talk about a system of particles. I am Professor Ricardo Gomes from the Physics Institute of the Federal University of Goiás. So consider a vector r as the radius vector of a particle from some given origin. So this is the position of the particle, and v is the vector velocity of the particle, and it is the rate of change of the position of the particle. So the vector velocity is the derivative of the position vector with respect to time. The linear momentum, p, of the particle is defined, this is a definition, as the product of the particle mass and its velocity. So the momentum p is the mass multiplied by the velocity. And the vector sum of all the forces exerted on the particle is the total force, and will be denoted by F. So the mechanics of the particle is contained in Newton's second law of motion, which states that there exist frames of reference, inertial reference frame, in which the motion of the particle is described by the differential equation force is equal to the derivative of the momentum with respect to time, so dp dt. And we can use this notation of p dot. This dot means the derivative with respect to time. Or, using this definition, we can write that the force is equal to the derivative with respect to time of this product, mass and velocity. In most instances, the mass of the particle is constant, and then the force can be written as the mass times the derivative of the velocity with respect to time. And this dv dt is equal to the acceleration a, where a is the vector acceleration of the particle, which is given by the rate of change of the velocity as with respect to time. And since the velocity is the rate of change of the position with respect to time, the acceleration is the derivative of the second order derivative of the position with respect to time. So in this case, the equation of motion is a differential equation of second order. So this is the equation of motion and is a differential equation of second order. Okay, so in any inertial reference frame, the motion of a particle is described by this equation here. However, even in classical mechanics, an inertial system is an idealization. In practice, we will deal with a coordinate system that is as close as possible to the desired one. For many purposes, a reference frame fixed in Earth, we can call it the laboratory system, is a sufficient approximation to an inertial system. In other instances, distant galaxies can be the reference frame. Okay, so now we are ready to talk about conservation theorems. These theorems indicate under what conditions various mechanical quantities are constant in time. So we're going to start with this equation, the force being equal to the derivative of momentum with respect to time, and we get from it a conservation theorem just considering this. If the total force F is 0, then P dot, or this derivative of the momentum, is 0, and then the linear momentum P is conserved. It is time independent. And this is the conservation theorem of the linear momentum of a particle. Again, if the total force F is 0, then the linear momentum P is conserved. Now, for the angular momentum, let's first define this quantity called angular momentum of the particle about point O, denoted by L, as the cross product between R and P, in this order, where R is the radius vector from O to the particle. So here we have the vector R, and for instance this is the vector P. The cross product between them is the angular momentum L. We also define the torque, and we will use N for the torque about point O, as the torque is equal to the cross product between R and the force F. So two definitions, and we need an equation analogous to this one here for the torque, and we can obtain using this expression, and I will use this equation in here. So doing this cross product, we have that the force is the derivative of this of the momentum with respect to time, and we will use this the following identity, vector identity. Consider the derivative with respect to time of R in a cross product with the momentum mv. It is obviously the velocity v, the derivative of R with respect to time, in a cross product with mv, plus R and the derivative of the momentum. So this term here vanishes because v is parallel to mv. And this guy here is the torque. Exactly what we have here. So this is another way to write the torque. The torque can be written as the derivative with respect to time of this product of R and the momentum. But we know what is the cross product with, of R with P. It is the angular momentum L. So the torque is the derivative of the angular momentum with respect to time. We can write it as L dot. Okay, so we have now a differential equation analogous to the force being equal to the derivative of the momentum with respect to time. And then we can get a conservation theorem from this equation. If the total torque N is 0, if this is 0, then L dot is 0, and the angular momentum is conserved. It is time independent, which is the conservation theorem for the angular momentum of a particle. Again, if the total torque is 0, then the angular momentum L is conserved. Now, for the energy, consider the work done by an external force F upon the particle in going from point 1 to point 2. And this is defined by the work from point 1 to 2 is the integral of the force in this product, inner product, with this displacement differential displacement ds. For constant mass, this mass can be written outside of the integral, and this is the force m multiplied by dv dt, and the differential displacement can be written as the velocity times this interval of time. And then we can see that dv multiplied by v, I can write it as a derivative of v squared. Take a look at this. If we consider the derivative of v squared with respect to time, this is equal, of course, v in the inner product with v, and this is going to be 2 times dv dt multiplied by v. So this term here is exactly what we have here, dv dt multiplied by v, and then I can write it as 1 over 2 d dt of v squared. And therefore, the work of the force in going from point 1 to point 2 is going to be m over 2 and v squared for point 2 minus v squared for point 1. If we call this quantity, this scalar quantity, mv squared over 2, as the kinetic energy T of the particle, then the work is going to be the kinetic energy on 2 minus kinetic energy on 1. So the work is the difference between the kinetic energies for the final and initial point. So if the force field is such that the work W12 is the same for any physically possible path between points 1 and 2, then the force is said to be conservative. So if we have a system like this, where the force field is the same, the work is going to be the same for any physically possible path, then we have a conservative system. So consider here point 1, point 2, and consider this the path, and we will have a work, W12, and if it is the same as this work here, different path, or for this other different path, then we have a conservative system. And the independence of the work on the particular path implies that the work done around a closed contour is zero, a closed circuit is zero. So the integral, considering a closed circuit of the work, force, and the displacement, is going to be zero because of the independence of the work with regard to the path. Of course, if we have dissipation forces, this is not valid. If friction or other dissipation force, Fd, are present, the system cannot be conservative. Why? Because the work of this dissipation force, Fd, ds, is always negative. The force is in the opposite direction of the displacement, always. And then this product is going to be always negative, from point 1 to point 2 and the way back. So the integral cannot vanish. So a necessary and sufficient condition that the work be independent of the physical path is that the force be written as the gradient of a scalar quantity v, which is a function of the position r. In other words, if the work is independent of the integration path between the points 1 and 2, it should be possible to express this work as the change in a quantity, a scalar quantity, that depends only upon the positions of the endpoints. This quantity may be designated by minus v, so that for a differential path length we have, so for this differential length, the work is going to be minus dv, the difference on this quantity v, or the component of the force along the displacement is going to be, like we're using here, the partial derivative, because v could, for instance, depend on other variables. So the derivative of v with regard to s, which is equivalent to the vector f as the gradient of this quantity v as a function of the position r. So again, a necessary and sufficient condition that the work W12 be independent of the physical path is that the force be the gradient of some scalar function of the position. Note that we can add to v any quantity constant in space without affecting the results. Since we are dealing with this variation, the gradient of the quantity v in space, if we add any quantity constant in space, it will not affect the results. Hence, the zero level of v is totally arbitrary. For a conservative system, the work done by the force is, if we use this for this expression for the force, then we will have an integration minus the integration from 1 to 2 of dv, which is, this integral is v2 minus v1. And the result, the work, is going to be v1 minus v2. This is our result here, and we already got this result. The work is the difference of the kinetic energy. So, using these two results here, so v1 minus v2 is going to be equal to t2 minus t1, or the kinetic energy plus the potential energy for the point 1 is equal to the same quantity, the kinetic energy plus the potential energy for point 2. And this is enough to get the energy conservation theorem for a particle, which is, if the forces acting on a particle are conservative, then the total energy, which is the kinetic plus potential energy, the total energy is conserved. It is time independent. So, a summary of this video, we discussed the fundamental principles of classical mechanics. We got 3 conservation theorems for the linear momentum, for angular momentum, and for the energy. We did all these in the Newtonian formalism. As reference, we are using the analytical mechanics from Nivaldo Lemos and classical mechanics from Goldstein et al. So I hope this video will be useful for you, and to watch other videos like this, please subscribe. Thank you very much.